of the lecture video. And it's time to talk about what is the unit circle. So the unit circle is a circle with a radius of 1, and it is on our coordinate plane, and it is centered at the origin of the coordinate plane. So all of our initial sides are anchored right at 0, 0 and extend along the x-axis out to 1, 0. And then the terminal side has been rotated around, and as it's rotated, it traces out a circle. Do copy down that definition. All right. And I put in this zoomed out unit circle just to give you kind of an idea of perspective on this unit circle. The unit circle is very small when compared to our coordinate plane, which we normally extend out pretty far. But a lot of action happens within this small circle here. We eventually want to get to the point where we can find all of the ordered pairs at very specific points around the outside here. But realize all of those ordered pairs are going to be fractions of a unit. The biggest unit we reach in the unit circle is right when we hit the axes, and we are at the point 1, 0 right here. As we trace the arc of this unit circle, these are going to be fractional x and y values, somewhere between 0 and 1 the whole time. So the unit circle is actually very small, even though we draw it pretty big normally. So our goal is eventually to be able to draw 3 lines into each quadrant of the unit circle, label them with degree and radian measure, and give the ordered pair of the point on the arc where those terminal sides intersect the unit circle. All of this you're going to be able to do from memory, plus even more by the end of this unit. All right, so hopefully you're taking notes on this. I would pause the video now, or pause the video when I stop talking here, and draw half of a circle. And you want to split up that circle into these angle measurements. 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees, 120 degrees, 135 degrees, 150 degrees, and 180 degrees. Now that's kind of tricky to do. So think about just first cutting it in half at 90, and then taking each quadrant and splitting it into thirds with these lines here. This line and this line, split that 90 into thirds, and then put in the 45 right in between them. Because this is not evenly splitting this into thirds. It's if you ignore this middle line here, these two split it into thirds, and then this line comes and splits this third in half. And so these wedges are a little bit bigger than these wedges. All right, so hopefully you've drawn that pretty well and labeled the degree measures. Now we want to go back and change them all into radian measures. So 0 degrees is 0 radians. No surprise there. What is 30 degrees in radians? Well, we can take 30 degrees and multiply it by pi over 180 degrees. And we get 30 pi over 180. We simplify that down. 30 goes into 186 times, so this is pi over 6 radians. All right. This one here, 45 times pi over 180 degrees. I'll save you the trouble. That's pi over 4 radians. And this one here, the 60 is a third of 180, so this is pi over 3 radians. All right. This we've already seen this one. 90 degrees is pi over 2. That's a very good one to remember. So you don't have to convert it each time. And now to keep going, we can just keep adding multiples to the ones we've already gotten so far. So if I add another pi over 3 to pi over 2, I'm going to get, well, I could think of this as 3 pi over 6. This is going to become 4 pi over 6, or 2 pi over 3. This one here, 135 degrees, becomes 3 pi over 4. 150 degrees becomes 5 pi over 6. and 180 degrees is pi. We already saw that one. That's a very convenient one. All right. So if you've got to convert them using this conversion ratio here, do so. Otherwise, eventually we do this so much that you'll have these ingrained in your memory. Yep, I think that's where we'll leave it for now. The more we practice, the more tricks I can give you for filling these out. Let's do the bottom side of the circle. So we already saw that 180 degrees is pi. 0 degrees is 0 radians. Let's keep rotating around. These amounts here are in increments of 30 degrees. Finally ending at 360 degrees, which equals 2 pi radians. So keep adding 30 degrees. This becomes 210. This one here is 240. Notice I skipped that one because that is halfway in between here. This is 270 degrees, 300 degrees. Skip this middle wedge. Get 330, and then 360 degrees. All right, to get that middle wedge, we could repeat the process but add 45 each time because it's 45, then 45, then 45, then 45 to hit that middle wedge. So 180 plus 45 is 225. Also another good double check because that's exactly halfway between 210 and 240. Over here, 270 plus 245 is 315. Again, that's exactly halfway between the 300 and the 330. And we got to convert each of these to radians. We can think about where we added 30 degrees, we're really just adding pi over 6 radians. So this one becomes 7 pi over 6. This one becomes 8 pi over 6, which simplifies to 4 pi over 3. This one becomes 9 pi over 6, which simplifies to be 3 pi over 2. 10 pi over 6, which simplifies to be 5 pi over 3, and 11 pi over 6, which doesn't simplify. And then double check, 12 pi over 6, that does simplify to be 2 pi. Okay, let's get this one here. We're adding pi over 4, so this becomes a 5 pi over 4. 6 pi over 4, which again simplifies to 3 pi over 2. And 7 pi over 4, which doesn't simplify. Okay, we've added in all of the angle measurements around our unit circle. And if you ever need one, you can always, getting the degree measure always feels a little bit easier because we're so comfortable with 360 degrees. Then you can always convert that by multiplying by pi over 180. Okay. In order to get the ordered pairs, we need to remember our special triangles. Likely you've seen this in geometry, but let's teach it again. So with our special triangles, we have the 30, 60, 90 and the 45, 45, 90. These triangles are so common that we've just memorized their side lengths. So if this side length here is 1, then the hypotenuse would be 2, and this side length over here is the square root of 3. We could get that by designating this as 1 and then using some just right triangle trig and then the Pythagorean theorem. But you can just trust me, plus trust what you remember about this. With the 45, 45, 90, we often say that this side length over here is 1, meaning that these have to be, actually no we don't, we say that this side length over here is 2, meaning that these side lengths are the square root of 2 and the square root of 2. That way a squared plus b squared equals c squared. 2 plus 2 equals 4, yep. But what we want to do is we want to change these so that the hypotenuse is always 1. And so we want to draw some similar triangles, but we want to divide everything by 2 so that we'll get a hypotenuse of 1. The reason that's good for us is because if we want to drop a triangle into our unit circle, well, the radius of the unit circle is 1. So we better have the radius of or the hypotenuse of our special triangle be 1. But it's as easy as just divide everything by 2, so we've made the hypotenuse of 1. And now this side length here is the square root of 3 over 2. And this side length down here is 1/2. Let's repeat the same here. Dividing everything by 2, we get 1 square root of 2 over 2 and square root of 2 over 2. All right, so I know it's a lot to memorize here, but hopefully we've seen these ones before, have them somewhat memorized, and then we can get to these ones by just dividing by 2. All right. And then there's the Mr. Olson's patented 90-90-0 triangle, which students love to debate is not actually a triangle, but I think it is a triangle with 2 right angles and a 0-degree angle. This triangle looks kind of like this. And I draw it as a triangle, even though this measure right in here is 0 degrees. And these are 2 right angles. This side length here is 0 units, and these lengths here are both 1 unit. Trust me, this triangle is going to be helpful to us. All right. So now it's time to fill in these ordered pairs around the unit circle. So the radius is 1. So if I drop in the patented 90-90-0, I'll see that the height here is 0, and the length to get out to this point is 1. All right. Or maybe you just think that that's obvious, that if you go just straight along this, where you're going to cross a circle with a radius of 1, will it be at 1, 0? But we will use the patented triangle eventually, trust me. All right, to get to this point here, well, its x value is right below this point. Oh, I should have said you're going to need to redraw this again in your notes unless you want to try to fit it all into one diagram. I think it's better as 2 diagrams. Anyway, if I drop a line straight down, then this triangle that terminal side creates will be a right triangle. This side length here will tell me the y value. This side length here will tell me the x value. So I'll just write that in, that this is the x and the y. Well, this length is 1. This is a 30-degree triangle, so I know these other 2 lengths because that's one of our special triangles. If this side length is 1, this side length must be 1/2. This side length over here must be the square root of 3 over 2. And that gives me the ordered pair, square root of 3 over 2, comma 1/2. Okay, this is going to get a little bit messy as I fill in these other special triangles. And try to keep it clear with different colors. But to get this ordered pair, I'm going to construct another triangle. This one, again, is a hypotenuse of 1. This angle measured down here is now 45, meaning this is our 45, 45, 90 triangle. And when this side length is 1, then these side lengths must be the square root of 2 over 2 and the square root of 2 over 2. Which give me my x and my y values. So I get square root of 2 over 2, square root of 2 over 2. All right, for this point right here, that's going to get real messy. Drop a line down, construct a right triangle. The hypotenuse must be 1 because the radius of our unit circle is 1. This is a 60-degree down here now, meaning that this is the 30 up here, meaning this side length is the 1/2. This side length over here is the square root of 3 over 2, giving me an x value of 1/2 and square root of 3 over 2. Okay, but we're done now because now we can just use the properties of symmetry to get the rest of them. This point up here, we can picture the patented triangle or just think it through. This point must be 0, 1. This point here is symmetrical to this point here over the y-axis, and when we reflect things over the y-axis, the sign on their x coordinate flips. So this becomes negative 1/2 comma square root of 3 over 2. This becomes negative square root of 2 over 2 comma square root of 2 over 2. Negative square root of 3 over 2 comma 1/2. And then over here on the unit circle, that's 1. So if I go 1 over, it's going to be -1 comma 0. All right. Let's keep reflecting these around the unit circle to get the bottom half. Go ahead and sketch this one here. We'll fill in these points here. They're easy to get. All right, so this one's been in this quadrant. Every ordered pair is negative, comma negative. So let me just think. This one is, I actually have to go look. It's this point, but with now a negative on both of them. So negative square root of 3 over 2, comma -1/2. This one's negative root 2 over 2, negative root 2 over 2, -1/2, negative square root of 3 over 2. And in this quadrant here, everything is positive, comma negative. So this point gets reflected over here, but it becomes a 1/2, comma negative square root of 3 over 2, square root of 2 over 2, negative square root of 2 over 2, square root of 3 over 2, -1/2. All right, so there's all the ordered pairs. Okay, there's only one more thing I have to teach you, and that's when I take the trig function of angles in these different quadrants, they always come out either positive or negative depending on the quadrant. All right, we can actually predict that, but without even knowing the angle, just knowing which quadrant it's in. So sketch a quick XY coordinate plane. Draw a triangle into each quadrant representing our terminal side and its X and its Y values. And we always, to get the X and the Y values, we always come back down to the X axis so that the height becomes the Y value and the base down here becomes the X value. And these do not have to be symmetrical. I can even draw this one a little bit bigger. It doesn't matter. All right. Now, the hypotenuse, because it is measured from the origin out, will always be positive. So we're just going to write hypotenuse on each of these, but it's a positive length for each of these. All right. In this quadrant, both the adjacent and the opposite will always be positive as well, because we're in the quadrant where both of those side lengths are positive. So this is going to be positive, and this is going to be positive. Our reference angle is right there in the middle looking out, so that's why this is opposite, this is adjacent. But over here, the adjacent will always be negative. Heading up, we'll have a positive opposite. Heading down, we'll have a negative opposite. Over here, this is a negative opposite. All right, so if I write out SOHCAHTOA, I can see that in this quadrant, opposite and adjacent are both positive. Hypotenuse is positive. Everything's positive, so they are all positive. All right. In this quadrant over here, opposite is positive, but adjacent is negative. So if you have an adjacent, then you're going to be negative. So sine is going to be positive. Cosine and tangent will be negative. I'm going to teach you a nifty mnemonic in just a second. Also, I'm just going to do sin. All right, stay with me. All right, here, opposite and adjacent are both negative here. So that's going to make sine and cosine both negative. But an interesting thing happens with tangent, because tangent has both opposite and adjacent. The negatives cancel out, and tangent is actually positive in this quadrant. And in our last quadrant, cosine is the only one that's still positive because it's only based off the adjacent, which is still positive here. So we'll say cosine is positive, and sine and tangent are negative because they both involve opposite, and opposite is negative down here. But here's how you're going to remember this. Just remember which one is positive, and then everything else will be negative. So in this quadrant, it's all. In this quadrant, it's sine. In this quadrant, it's tangent. In this quadrant, it's cosine. And that, if you can just remember that, you can remember all the rest of it. And here's a really nifty mnemonic for this. You just write the first letters, A, S, T, C, and you fill them in like we're numbering our quadrants. And then as you go around this way to remember ASTC, you say all students take calc. And that gives you the mnemonic to remember which one is positive. Okay, this was just our intro. I'm going to be explaining this more and more in future videos. So hopefully you paid attention. There's still a homework help video to help you with the homework. But don't freak out if you're still not understanding 100% of this. Hopefully you've got some good notes, though, that you can reference back to as you understand this better and better. All right, have a great rest of your day.